Hello, my name is Ben Klugszewski. This is Physics 2212 and Lab 3, bar magnets. Alright, first up in this presentation I'll be taking you through four main parts. First of all, we're going to have the introduction. It's going to be a description of the lab and fundamentals. Second of all, we'll have observations, data, and calculations, which will just be setup, results, and analysis. Third of all, we'll have Glowscript, which will be the actual coded Python model. And finally, we'll have a few final questions and final thoughts on the matter. Alright, introduction. So the goal of this experiment is to determine the magnetic dipole moment of a supplied bar magnet using concepts such as distance dependence. Furthermore, we'll create a visual representation via a coded model in Glowscript. Specifically, we want to calculate the magnetic field at a certain point and compare that with our Glowscript model and the data we found directly from the measurements. The overview. In this experiment, we're going to first collect data using a magnetometer app to collect data on the magnetic field produced by a simple bar magnet. With said data, we will calculate the magnetic moment, calculate distance dependence, and calculate the magnetic field at theoretical positions in space. In this instance, it's going to be 45 degrees off the x-axis with Glowscript and compare it to actual recorded data. Alright, in this experiment we used a few formulas. Formulas 1 and 2 describe the magnitude of the field due to the magnetic dipole. Formula 3 deals with the linearizations of our data. Formula 4 describes the magnetic field of a dipole at any given location, which will be used in the computational model we'll see later. Now we had to make a few assumptions for this experiment. Primarily two. First of all, we idealize the bar magnet as a perfect magnetic dipole, and second of all, we assume that the measurements displayed by the phone magnetometer were accurate and reliable. Alright, what we observed and what was true. When the magnetometer is far away from the magnet, it does indeed measure a near zero magnetic field in x direction. However, it's incorrect that as the magnetometer moves close to the magnet, the measured x component of the magnetic field will not decrease. The position of the magnetometer also does have an effect on the measured x component of the magnetic field. Furthermore, as the magnetometer moves close to the magnet, the measured x component of the magnetic field does increase. Here are our calculations. On the right, you'll see a graph, a logarithmic graph of the data that I collected in the experiment. And this is a logarithmic graph of distance dependence, where y equals negative 2.51, x minus 13.8. Negative 2.51 is used as n, and we'll use the Biot-Savart law. We can calculate magnetic dipole moment using r as 1 meter, b subscript x is negative 13.8. We can use one of the formulas outlined prior to find k. Then using all these values, we can plug in and solve for mu, where we obtain mu as 5.078. Now here's the Glowscript model. As shown on the right, the white bar in the center is the idealized version of the bar magnet, whereas the red arrows represent magnetic field in line with the axis, green arrows represent magnetic field perpendicular to the axis, and the blue arrow in the top right corner represents the net magnetic field at that point in space. That is the primary value that we were calculating for in this lab and what we'll be comparing. All the calculated values are shown below in that text. The most important one is, again, the second from last, the magnitude of B at 45 degree distance at distance D, which is that value 1.08 times e to the negative fourth. Alright, comparing results. Directly measured from the data, I obtained a result of 1.11 times e to the negative fourth, whereas via the Glowscript computational value, I obtained a magnitude of 1.08 times 10 to the negative fourth. Comparing these two values, we see that this is incredibly similar, to the point where it's an uncanny difference. So it can be said that this calculations was quite accurate. Realistically, this computation wouldn't yield such an accurate value But either way, does seem to be a good representation of what we wanted. Finally, we have the what ifs and whys. What if you hadn't oriented your experiment to compensate for magnetic north, and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So, assuming we did it as like detailed above, the logarithmic approximation graph would retain the same values. However, values for x components of the magnetic field would change. Initially, the experiment was designed to negate Earth's magnetic field. That's why we lined it up due north. And if that factor were removed, the values would be affected. However, again, the logarithmic approximation graph would remain the same. Now, what if you were to stick two identical magnets together, end to end, and run the experiment again? How do you expect your measurements to differ? Ultimately, the overall field would be stronger, and the values would increase in magnitude. Alright, thank you for listening to my presentation.